So we are discussing chemical bonding, and let's deal with the concept of hybridization. Well, we'll give you complete details of the concept of hybridization, but what is the necessity of actually having this concept will be the base for understanding why the concept of hybridization has been introduced, right? Before I go there, I just wanted to tell you that, when we deal with chemical bonding, your perception of the bond must change. Well, I wanted to remind you in all the sessions this particular point, right? When we say of a bond is basically a force, right? It is a force that binds two atoms or ions in a molecule, you must understand. So the bond is basically a force. So that thinking you must be developing throughout the chapter. So please understand that yes, you might be having some understanding of a bond, but these are all for having a perception. But actually, technically speaking, yes, a bond is basically a force. When you say force in chemical bonding, I think you have several types of forces in chemical bonding. And the most convincing for me is, of course, what electrostatic force you must understand. Right? So electrostatic force, when you say it is between oppositely charged ions, because that will be prevailing only in oppositely charged ions and nowhere else. So what happens is when you're dealing with the ionic bond, where you have electrostatic force between the oppositely charged ions, it seems to be absolutely convincing by default. You must understand. By default, it seems to be absolutely convincing for me because that force is binding these two positive and negative ions together, and then fine, the bond is established, and the strength of the bond is derived by the electrostatic force itself because you have oppositely charged ions. So the most convincing of all the bonds is basically what? Ionic bond, you must understand. Yes, we have dealt that in detail. Right? Now the question arises, if you apply the same thing to covalent bond, well, covalent bond is formed by sharing of an electron pair. A bond is formed by sharing of an electron pair. We can understand that definitions are told in our school by our respected teachers, but a covalent bond formed by sharing of electrons is fine. But the issue is where does the strength of the covalent bond come from? Similar explanation, what we have given for ionic bonding must be given for what? Covalent bonding. Where does the strength of the covalent bond coming from? You said that the atomic systems are not having octet, so both have come together to share an electron pair and then satisfy the octet and the bond is established. Fine, that is fine for a perception, but we can't be hanging on to that. We have to give explanation why and where the covalent bond strength is coming from. Right, for that I think we gave a great explanation given by Linus Pauling and by introducing the concept of overlapping. Well, the concept of overlapping, before the concept of overlapping, it was told that the atoms are overlapping with one another. The atom doesn't overlap with one another. It is the orbitals inside the atom that are actually overlapping with one another and holding these two atoms together. That should be the covalent bond formation. So basically one of the features and one of the highlights which can take it forward forever in our life in chemistry is basically the introduction of the concept of what? Overlapping. That cannot be discounted throughout chemistry. So one of the biggest highlights of Linus Pauling is the concept of overlapping. Now even I vote for that for the simple reason that when atomic systems are participating in bonding and the orbitals in which the electrons have opposite spin have participated in bonding, then what they are doing is they are making themselves delocalized. They are making themselves delocalized. When they make themselves delocalized, I think you're running through a larger volume. When you're running through a larger volume, you try to lose energy more. When you lose energy more, you gain stability, because stability and energy are inversely related. You must understand that, right? So delocalization happens when the concept of overlapping has been introduced. When delocalization is happening, that's where energy is lost, and thereby you gain stability. That's where the strength of the covalent bond has been attained. This is the discussion what we are making yesterday. So remember one final point before I get into the concept of hybridization is the strength of the covalent bond is achieved by the concept of overlapping proposed by what? Linus Pauling. That is the biggest merit of his the valence bond theory, is the introduction of the concept of overlapping. You must understand. So while dealing, now in today's session we will actually introduce the concept of hybridization, and then we'll go in for the applications which are required for your exam. Now, why the concept of hybridization? That forms the basis to understand the hybridization itself. What is the necessity to have the concept of hybridization when someone has proposed the valence bond theory is the issue, right? So as I said, whether everyone will have merits or not, we don't know, but definitely everyone will have some flaws. Everyone will have some demerits, that's for sure. That's for sure. So even Linus Pauling has some serious drawbacks, very, very serious drawbacks. In fact, yesterday I was, in the previous session, I was actually telling some of his explanations seem to be absolutely ridiculous, silly, right? So it necessitated for having another theory that will actually take care of all the drawbacks which is given by what valence bond theory. One of the drawbacks I would like to brief is this. Whenever a P is projected, P projected onto S, P projected onto S, the P orbital projected onto S, the direction not fixed. The direction of the projection of a P vector or the P orbital onto S is absolutely not fixed. We need to rectify this because whenever P orbitals are involved in bonding, the bond angle remains to be 90. That is another biggest flaw which is ridiculous and silly, right? So the P orbital onto S direction is not fixed. This is the S, this is the P, this is the P, this is the P. Which way it is coming, we never know. We never know. That direction is absolutely not fixed. And whenever the P orbitals are involved in bonding, like you have X, Y, Z, the bond angle remains to be absolutely 90 degrees is absolutely ridiculous, silly. So what you're telling me basically in valence bond theory is you're telling that, in all the sixth group hydrides where ammonia, PH3, ASH3, SBH3, all the bond angles are 90 degrees because in all the P orbitals are involved and they are mutually perpendicular. These things are not taken care of by the valence bond theory which I was explaining in detail in the previous session. Right? You can go through that session for detailed discussion. Well, in fact, as I consider it to be a serious flaw, the other biggest serious flaw is basically at the nick of the moment. At the nick of the moment when I was about to participate in bonding, these issues are cropping up. Like, the P orbital onto S is not fixed, what to do? At the time of bonding, if you can crop up all these discussions like, I'm unable to fix the direction of the P orbital onto S, and thereby the consequence is very clear that you are not in a position to fix the bond angle. When you're not in a position to fix the bond angle, you're not in a position to tell some comments on the shape of the molecule. You must understand that, right? So to rectify two things, which I would like to write it on the board, we propose the concept of hybridization. You must understand that. But one thing I wanted to make clear, and I want the attention of everyone, is basically we are here not to prepare compounds. We are not preparing any compounds. We are not preparing any molecules here, sitting here. Molecules are already there. Their bond angles are also determined. You're not doing determination of bond angles. No, absolutely not. We are not doing that, nor we are preparing any compounds outside. Ammonia is very much there. Water is very much there. H2S is very much there, right? The only thing what we are doing is we are just catering and explaining a theory which will be convincing to explain why the bond angle is 104, 106, 109, 28 minutes or whatever. Right? And why the shape is pyramidal, tetrahedral, pentagonal bipyramidal, or whatever the shape it has attained. We are trying to place a theory to actually support that particular shape or the bond angle. Remember this. The discussions what we are making, whether it's a valence bond theory or hybridization, they are not the methods of preparations of molecules. Molecules are already there. We are trying to propose a theory which will explain and reconcile the bond formations or the bond angles formations that the molecules have been possessing. Keep that in mind, right? These are no methods of preparations, you must understand, right? So let's get into the concept of hybridization today and today's session. And I would like to write why the necessity of the hybridization here. Observe carefully. The following drawbacks the following drawbacks which I'm listing it out, right, necessitated another theory. And what are the following the drawbacks? Number one, p orbital projection onto S is not fixed. It's absolutely not fixed. P orbital projection onto S is absolutely not fixed. So whenever P is trying to get into the S, its projection is not fixed. That's number one. I gave details of that. Second one, whenever p orbitals which are mutually perpendicular, right, you must understand, whenever the p orbitals which are mutually perpendicular, involve in bonding, the bond angle remains to be 90 degrees. It remains to be 90 degrees, which is ridiculous and silly, which I don't agree at all, completely, I don't agree at all. So what prompted me to propose the concept of hybridization in this session, which I strongly believe is this: you have some flaws, serious drawbacks in the valence bond theory. That is, the projection of P onto S is not fixed, and whenever the P orbitals are involved in bonding, the bond angle remains to be 90 degrees. These seem to be corrected immediately, right? One more thing which I would like to add, right? We said, it is hard to believe someone is telling me, it is really hard to believe someone is telling me this, right? It is only that orbitals in which the electrons possess opposite spin, only those orbitals in an atom in which the electrons possess opposite spin shall participate in bonding, is something, really hard to believe, right? And what is hard to believe here is basically, imagine that one orbital has an unpaired electron, right? The other has an unpaired electron. They are approaching each other. Very close to one another. They're basically very close to one another, and they participated in bonding. Now my question is, how can you discount the influence one electron is having on the other electron when the two atoms are approaching each other? Can we actually discount the influence of some of the electrons which are not participated in bonding? They are in the previous shells, not the outermost shells. And when the atoms are approaching, there will be some sort of influence, I'm sure about it. Some sort of influence of the orbitals which are present in an atom, which have not participated in bonding, but when the atoms are coming close, yes, there will be influenced, because there is a difference between you being far away and when approaching each other, each and every electron in the atom and each and every electron in the other atom which are participating in bonding gets influenced. This influence of each and every electron in an atom has been discounted. It's completely discounted. It's discounted. Can we discount it is the issue? Yes, it is discounted rather. But the obvious thing is, which I don't believe, this influence must be considered, because that will be having a bearing on the properties of such compounds if you try to discount it. You must understand that. So 3 things, 2 I have written. 1, the projection of P onto S is not fixed. And whenever P orbitals are involved in bonding, the bond angle remains to be 90 is ridiculous. That means that you're telling me that the 5th group hydrides are all having bond angles 90 and the 6th group hydrides all having bond angle 90, and whenever p orbital is participating in bonding, the bond angle remains to be 90 is silly, ridiculous. The other thing is discounting the influence each and every electron will be having on the other electron when the atoms are approaching each other seem to be it's not a good idea, because it will have a bearing on some of the properties which we'll be dealing once we go into further depth of this subject, right? So based on these two drawbacks, well, I introduced to you the concept of hybridization. Let us go and check what exactly is hybridization. Observe carefully now. Now remember, this last minute pushes, I was about to participate in bonding and someone is coming and telling me that the direction is not fixed. Which way to come? Which way to come? Is something ridiculous. At the nick of the moment, you tell me that from obtuse angle, from the perpendicular, you obtuse angle, acute angle. And when I was just participating in bonding, all this nonsense is cropping up. So what a hypothetical theory is suggesting is, well, I have an idea. What we will do is, before participating in bonding, I draw the attention. Let us have a hypothetical theory where before participating in bonding itself, right, the positions are fixed. Bond angles are fixed, shapes are fixed. Instead of coming and telling me, sir, I'm ready, now I'm in excited state, the p orbital is coming onto the s, and the direction is not fixed, as I come obtuse, acute, right, 70 degrees, 80 degrees, these questions arising at the nick of the moment, and then you say that the projection of p onto s is not fixed, bond angle not fixed, and shape is not fixed. Instead of that, I think it's better to have a theory, a hypothetical theory where before participating in bonding itself, right, the orbitals sit in certain positions, bond angles are fixed, structures are fixed, shapes are fixed, everything before what? Bonding itself. If that can happen, such a theory would be a fine theory, and such a theory is basically, such things are taken care by the concept of hybridization. So basic aim of proposal of the concept of hybridization is, the basic reason why I propose is to get better directional orbitals, so to better directional orbitals. Better directional orbitals in the sense he is actually telling us that, before bonding, the bond angle is fixed and the projection is fixed. You don't face the problems like the p onto s. So to get some orbitals such that they have better directional properties, right? Directional properties in the sense that before bonding itself, everything is fixed. Before bonding itself, everything is fixed. You must understand. So what is hybridization? Right? Let me define this. And I put it in inverted commas, and it is basically hypothetical. It's a greatly convincing theory, but it is absolutely hypothetical. It is absolutely hypothetical, greatly convincing. Even though it's hypothetical, we are actually catering to explain some bond angles and shapes through this theory. So I say it is basically what convincing. So what is this? It is basically hypothetical. I'm defining what is hybridization. I define what is hybridization. So it is hypothetical intermixing I would like to underline. It is a hypothetical intermixing of atomic orbitals, right? So it is hypothetical intermixing of atomic orbitals, right? Where in an atom, hypothetical intermixing of atomic orbitals in an atom, right? So in an atom, before participating in bonding itself, everything is happening. Everything is happening before bonding. What is happening within the atom before bonding is basically hypothetical intermixing of atomic orbitals in an atoms to generate entirely. Look at this. The hypothetical intermixing of atomic orbitals to generate entirely new set of orbitals called hybrid orbitals with better of directional properties. This is what is called hybridization. This is what is called hybridization. You must understand. To understand the complete depth of hybridization, you must be understanding few things. You know, as I said, I was just about to participate in bonding. I was ready, but in the last moment, you tell me that from which direction you need to come, as it happens in p orbitals onto s. Well, we are not in a position to determine at the 11th minute, right, then which or where, from where and which direction you need to come. Then in such cases, you face issues. So to rectify that issues, what I'm telling is, first of all, I must be ready for bonding. I must be ready for bonding. The orbitals must be ready for bonding, sitting in certain positions, fixed. Then invite the partner. That is a simple idea of hybridization. Instead of partner approaching you, you both are discussing, right? The orbitals are discussing which position I need to come at the nick of the moment. What you do is better, before participating in bonding, the orbitals sit in certain positions. The orbitals which wanted to participate in bonding, they must be sitting in positions, bond angles are fixed, and then invite the partner for overlapping. That is the idea. That is the idea of hybridization. Instead of calling the orbital first and asking to overlap and then find a problem that from which direction I need to come, rather, before participating in bonding itself, the orbitals which wanted to participate in bonding better be ready. Sit in a direction in the sense your bond angle is fixed. Everything is fixed, then call the partner. You invite the partner which you wanted to participate in bonding with, the orbital, and then go for bonding. Then you don't face that last minute issues of which direction you wanted to come. So simply speaking, everyone must understand that hybridization occurs before bonding. The hybridization occurs before bonding. That is a critical point you must be inducing into your mind. It is not during bonding or after bonding. It is basically happening before bonding itself. Where? In an atoms. The atom has still not participated in bonding at all. Before bonding itself, everything is happening. Now what is happening? This is happening. Watch. It's intermixing of atomic orbitals in an atom. The intermixing of atomic orbitals. Now what are the atomic orbitals which you know? Is SPDF. These are the atomic orbitals. You must understand. So before bonding itself, the intermixing of atomic orbitals in an atom. Once you intermix a Cadbury and a Nutrient chocolate, you get a chocolate which will be called Cadbury Nutrient. You're mixing it off, right? So Cadbury Nutrient chocolate is something a hybrid. You have hybrid cars these days. You have petrol as well as what? Your gasoline, the electric cars, they have a switch, seamless switch, where you can switch on your electric as well as get into what? A petrol mode. It's a hybrid thing. It's absolutely hybrid. Similarly, the atoms have still not participated in bonding at all. Yes, they have the intent of participating in bonding. But before bonding itself, everything is ready. How are you getting readied? This is how you are getting readied. It is hypothetical intermixing of atomic orbitals in an atom to generate entirely, when you mix off S and P, SPD, then you generate a separate set of orbital which has a better directional properties, and it will be called SPD. You don't call S because S is mixed with P. If S is mixed with P, it's called SP. So you must understand. So one critical point, every time I have wanted to remind you, this concept of hybridization is not a method of preparation to prepare compounds. No, it's not a method. Compounds are already there. We are trying to place a theory which will actually reconcile to the bond angles and the structures of the compounds which are already available. Remember that hybridization occurs before bonding. And what is happening before bonding? It's hypothetical intermixing of atomic orbitals in an atom to generate entirely a new set of orbitals called what? Hybrid orbitals. And the biggest feature of this hybrid orbital is, it has a better directional properties. When I say better directional properties, I'm actually telling you, it's implying that before bonding itself, the bond angle is fixed. Direction is what? Directional property is what? You're going through a certain angle. You're going through a certain direction. You're going through a certain direction. You're overlapping through a certain direction, and the direction is fixed. When I say the direction is fixed, the bond angle is fixed. So the entire hybridization is to get better directional orbitals. And it happens, all this is happening before bonding. Before I invite the partner for bonding, I'm getting readied. I'm basically getting readied for the bonding. You must understand. How did I get readied? I intermix the atomic orbitals to generate entirely a new set of orbitals called hybrid orbitals with better directional properties. Now what I'll do, I will see this definition, I will apply this definition to the orbitals. Let us check how the hybrid orbitals look like. Look into this. Intermixings, look at this. Combinations. Intermixing combinations, right? Intermixing of what? Atomic orbitals. Now, what are the atomic orbitals which you know? It is SPDF. So what we will do, the first intermixing is this. 1s and 3p's. One s orbital and 3p orbitals. And remember, all this is happening in an atom, all this is happening before bonding. So I'm getting ready to participate in bonding, and my bond angle will be fixed. So see, look at the first way of getting readied. There are several combinations, because once you have SPDF, 1s and 1p can combine, 1s and 2p's can combine, or 1s and 3p's can be combining it. Right? And it is the first case which I'm telling, 1s and 3p orbitals. Let me draw. Your s orbital is spherical. This is the s. This is now intermixing with the px, py, and the pz. Remember this. 1s and 3p orbitals is the first combination what we are speaking. Here is it. 1x, px, py, pz. So these three, I call this to be 3p orbitals. So I am getting readied myself. I didn't call my partner yet. I didn't ring. So within the atom, to cater to the needs of explaining the bond angles of certain molecules, I am proposing a hypothetical theory where I say it is 1s and 3p orbitals, they are combining. And look into this. When they combine and intermix, when they intermix, look into this, what you're getting. When they intermix, this is how oh man, this is slightly fat. You'll have a tail, of course, you'll have a tail. Let me draw properly. Now look into this, 1 Cadbury and 3 neutrons, you'll basically get 4 chocolates, because it's 1 Cadbury and 3 neutrons. It will generate total number of orbitals that are generated are 4, right? Because the 4 you are intermixed, the hybrid orbitals also will be 4. So the total number of hybrid orbitals generated will be equal to the number of atomic orbitals involved. So I draw 4 hybrid orbitals now. Look into this. 1, This is the 1 sp3. This is the 2 sp3. This is the 3rd sp3. And this is the 4th sp3. Now if you ask me what are those? This is one sp3 hybrid orbital. And it has acquired the shape of S as well as what P. That means the P is actually slimmer. These three are slim. So pure p orbitals are absolutely slim. And the s orbital is spherical, it is fat. So slim versus fat, if you try to mix it, the sp3 orbital will slightly have the shape of an S, a little bit fatter, but not exactly fat as S, but at the same time has the shape of P. So you must understand 1s and 3p's, when they combine, you will generate 4 sp3 hybrid orbitals, 4 sp3, and the hybrid orbital will have the shapes of S, which is slightly fatter, at the same time acquire the shape of P, which is dumbbell. So S is fatter and the P is dumbbell, then you have to imagine, it's hypothetical, right? It's hypothetical imaginary thing. So I have 4 sp3 hybrid orbitals. 1, this is sp3, this is sp3, and this is sp3. I generated 4 sp3 hybrid orbitals, right? All this is happening before bonding. So this is the first combination what I have. 1s and 3p orbitals, 1s and 3p orbitals generate 4 sp3 hybrid orbitals. 4 sp3, HO is hybrid orbitals. So if someone is asking you how many hybrid orbitals can be generated, you tell them that it's a number of atomic orbitals that are involved. Here the total involvement is 1s and 3p, so you generate 4. And all the 4 are sitting in certain positions. Look here, the bond angle is fixed. And the bond angle is exactly 109 degrees 28 minutes. Wow. What is wow here? I have still not participated in bonding. I have still not invited the partner. But still the bond angle is fixed. Such a theory where within the atom, intermixing of atomic orbitals take place to generate an entirely new set of orbitals sitting in certain positions with better directional properties is called hybridization. That is the whole thing about. So to get better directional properties before participating in bonding, I didn't call the partner, but still I'm ready with a bond angle, sitting at a bond angle of 109 degrees 28 minutes. So now what I will do is let us actually be specific. What we will do, the mixing, this is the first one, the sp3, the sp2, and the sp. I propose to you 3 combinations for you. When you have SPDF, you will always have 3 combinations, right? And I wanted to put what are all the features, the bond angles which you have acquired before bonding and all, and compare one with the other. And remember always in your mind, whenever you are dealing with hybridization, it is always about participating. All this is happening before bonding. Before bonding, you must understand, right? Let's take the case of sp3. So here what happens? 1s and 3p's. I would like to write THRED and ON, because if you write 3p, if you write the numerical, it says it is only one 3p orbital. So be clear. So very consciously, I'm writing 1s, ONE and THRRE. Right? 1s and 3p's. And 1 plus 3 is 4. So you get 4 sp3 hybrids. You get 4 sp3 hybrids. 1 Cadbury and 3 Newton will give you 4 chocolates. And 4 sp3 hybrid orbitals. And all the 4 will look like this. Two, 3, and 4. Don't forget the tails. These are the 4 sp3s, sp3, 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 and the sp3. Remember that. And here the bond angles fixed, and it is 109 degrees 28 minutes, and the shape is also fixed. The tetrahedral. You must understand. The shape is also fixed. It is tetrahedral. What is very strange, The only thing left is I am ready before bonding. Now just the partner has to come and overlap, that's all. You get overlapped into this, then the molecule is formed. That nuisance of, just before bonding asking people that, the P projection onto S, which direction I need to come, acute, obtuse, what to do, which direction, bond angle not fixed, and all these things have completely ruled out here. So I'm sitting now in a direction, and the direction is 109 degrees 28 minutes, and the shape is also fixed, that is tetrahedral, and the first type of combination is ONE1S. It's 1S, ONE1S. It's not 1S. If you say 1S, it is 1S. ONE1S means it is 1S orbital. THREP, you need to write it because it is 3 p orbitals. It can be 3 2p's, 3 3p's, 3 4p's, 3 5p's, or something like that. So don't be casual in writing, 3STHREE. Remember that, right? You generate 4 sp3 hybrid orbitals. They have better directional properties. And look into one of the sp3 hybrid orbital. It has the shape of S, slightly fatter, but at the same time you can't even divorce the shape of S. This is one sp3. It has both what S characteristics as well as what P characteristics. And if you wanted to calculate the S and P characteristics, of this, then I would like to say you have sp3, right? sp3. So total is 4. So you'll have 1/4 S character, that is 25% S character, and you have the P character 3 P's. So you have 3/4 P character, that is 75% P. That's why it more looks like a P, less looks like an S. So if 3 p orbitals are involved, the more dominating will be P in the hybrid and less dominating will be S. You must understand, right? That is about sp3. Same thing, let us write it in case of sp2. So here 1s and just 2 p's. 1s and 2 p's. It is here 1s and 3 p's, here 1s and 2 p's. Then you have 1 plus 2. It is 1 Cadbury, 2 nutrients. So you'll have total 3 chocolates. 1 Cadbury, 3 nutrients. Right? So remember that it's 1s and 2 p's. 1 plus 2 will be 3. Is it S? No. Is it P? No. Then what it is? sp2 hybrid orbitals. You must understand. sp2. So it's basically 1s and 2 p's. 1s and 2 p's. They intermix and generate 3 sp2 hybrid orbitals, and they look like this. Much fatter. Don't forget to draw the tails, please. Those are sp2s, and this is sp2. This is sp2 and this is sp2. You must understand. All the 3 are sp2s. And the bond angle between them is 120 degrees. So if I can write some of the features of this, bond angle 120 degrees, and the shape is basically triangular planar. That means that you have 1p this way. If I can put the board like this, if I catch this board and pull it off, then they are actually on the same plane, one sp2, the other sp2, the other sp2, right? Planar triangular. Its total is 360 degrees in a circle, and the bond angle is 120 degrees. So I can simply say shape is planar triangular. That is the shape, and everything is fixed. Strange. That nuisance of last minute nuisance of from which way to come. The partner is asking me and I am ready. Which way to come? Obtuse is not fixed. Right? Perpendicular is not fixed. Acute is not fixed. We are facing issues. So to avoid all these issues, here is the concept of hybridization. All this is happening before bonding. Before bonding, 1s and 2p's might combine, or 1s and 3p's might combine, depending on which molecule you are actually wanted to reconcile, to explain. So sometimes it is 1s plus 3p's, sometimes it is 1s plus 2p's, and if it is 1s plus 3p's, this is the directions, and if it is 1s plus 2p's, it is 3sp2's. And in 3sp2's, you will have 1/3 S character and 2/3 P character. So S character is 33% in what? sp2. Here it is 25%. There the P character is 75%. Here it is less than that, that is 67% what? P character. You must understand that. All this is happening before bonding itself. Before bonding itself, we are trying to reconcile, explain some theory which will be convincing without any flaw, to explain some molecules which are already there with bond angles 108 degrees 28 minutes, some molecules. Some molecules are there sitting outside like boron trichloride, 120 degrees. How will you explain? You can't explain boron trichloride using valence bond theory where the bond angle is 120. You cannot. You cannot explain methane with 109 degrees 28 minutes using valence bond theory. What will you do? I propose a theory which is hypothetical. This last minute nonsense, nuisance of people asking me which way to come. Better I be ready before bonding. Be getting readied before bonding itself is hybridization. And for getting ready, you have several combinations. It can be 1s and 3p's, 1s and 2p's. This way. Right? And then coming to the last one. That is 1s and 1p. It's like one Cadbury, one Nutrin. So you'll have two chocolates, which will be Nutrin as well as what? The Cadbury. Right? It's like that. So it's only 1, 1. So 1 plus 1 is, you'll get 2 sp hybrid orbitals. 2 sp hybrid orbitals. And here the bond angle is 180 degrees and the shape is also fixed. That is linear. The shape is also linear. It is the case of 1s and 2p's, sorry, 1p. So this is 50%, this will be 50%, and the hybrid will look like 50% S, 50% P. So it's somewhat like this. It's almost a circle, but not a circle. This is 1s. This is 1sp, hybrid orbital. And you have the another because you have 2sp hybrid orbitals. This is 1sp hybrid orbital I'm drawing, which has the shape of S as well as P. 50% S, 50% P. But it is involving 1s and 1p, so you get 2sp orbitals sitting in a certain angle. And the angle is this. Watch. This is another sp orbitals. So basically I can simply say this is 1sp, this is 1sp. You must understand these are two sp hybrid orbitals. Here you have 50% S character and 50% P character, and both these are sitting at a bond angle of 180 degrees. So the shape is fixed, the bond angle is fixed, everything is fixed. Strange, everything is happening before bonding. All this is happening before bonding. This I wanted to repeat n number of times. Hybridization is no method of preparation. There is absolutely no method of preparation for molecules. Molecules are already there. They are already there. Their bond angles are known. Only thing is we require a theory which will explain why such a thing is happening. After all, we are science people. We must have rational thinking. If you just hang on to valence bond theory, you cannot explain molecules with 109 degrees 28 minutes. You cannot explain which is 120 degrees, or you cannot explain 180 degrees and the shape is linear. You cannot. So that is the significance of what? Significance of what? The concept of hybridization you must understand. Now, only it is sp sp2 and sp3 or several other hybridizations are also there. Yes, we do have several other hybridizations also, but remember that visualizing them and drawing it on the board would be a difficult idea, but anyway, we would like to list it out. For example, watch carefully here. It will be sp3. In fact, let me start off with S. sp, sp2, sp3, sp3d, d2, d3. These are the things which are most obvious and distinct in chemistry, not beyond that. Now I leave it to you. 1s and 1p I can visualize. 1s and 2p's I can visualize. It will have 1/3 S character, 2/3 what? P character or something like that, right? Right, the difficult part is, we have several types of hybridization. Some we visualize, some we cannot. But remember that, that this is the difficult part, right? Which molecule will be undergoing which hybridization for the student who is preparing for the exam? Well, I would like to make it easy. There are two ways. I propose to you a formula, but at the same time, let us actually see what are examples of each type of hybridization. If it is sp, it is beryllium chloride, which is not explained by what? The valence bond theory, where he was struggling to explain that p orbital projection onto S is not fixed and all these kinds of things, right? Beryllium chloride is example, beryllium fluoride is example, and even acetylene, C2H2, which is acetylene, will be forming an example. You must understand that, right? So, in beryllium chloride, beryllium fluoride, and acetylene, the central atom is that which is getting readied before participating in bonding, in which hybridization takes place. The central atom here is beryllium, and what? The carbon, right? In which it is getting readied before calling the partner, that is chlorine, fluorine, and hydrogen. So those are the examples. For sp2, the best example is ethylene, C2H4, you must understand. And the other example is boron trichloride or boron trifluoride. That can be taken as an example. Now, the difficult part for the student is how we can judge instantly, right? If I are given a set of molecules like this, which hybridization it is happening here in the central atom, how to judge it? Can we make it easy? Yes, we can make it easy. I propose a formula to you. Yes, we will discuss that. But let me give some examples first. The sp3, the basic thing is methane, that is CH4, ethane, C2H6, and in sp3, the best examples for this is, even for sp3, all alkanes, in fact, all alkanes in organic chemistry will be undergoing what? The sp3 hybridization. You must understand that. Right, for sp3d, the best example is PCl5. sp3d square, the best example is sulfur hexafluoride. D cube is IF7. Iodine heptachloride, these are the examples. Now, S and P, I can visualize 1s and 1p, I can draw a diagram. 1s and 2p's, I can visualize 1/3 S character, 1/3 P character, 2/3 P character, and we can draw a diagram on the board, which I have drawn already. sp3, it is 1/4 S character, 3/4 P character, I can visualize and draw. But coming here, 1s, 3p's, and 1d. Now, D is double dumbbell, P is dumbbell, S is spherical. Now you think how the diagram will be. You need not draw, but if you wanted to visualize through a computer aid, you can do it. You are welcome to do that. Similarly, 1s, 3p's, and 2d's. 1s, 3p's, and 2d's. 2 double dumbbells, 3 dumbbells, 1 spherical. Mix it off to generate an entire set of new orbital. And if you wanted to visualize, you're welcome to do that. Similarly, this, right? So better visualize these, but I think the hybridization will be extending further. Of course, it will extend further like this. You must understand this, right? Right. The toughest part now, how do we judge in the exam? Suppose for an exam writing student, how does it judge which hybridization is taking place in which molecule is the issue. Is there any way out? Is there any formulae? The answer is yes. You have a formulae. You will definitely have a formulae. Let us see this, right? Observe carefully. Here is, to know which hybridization is taking place in a molecule or radical, in a given radical or whatever, or in any species. How do we know which hybridization is taking place in a given set of compounds? Then what do we do? So it's all about, you need to know first number of hybrid orbitals generated. That is H. If you can know the number of hybrid orbitals generated, then you will fix the hybridization. You can fix the hybridization. So if someone wanted to know which type of hybridization is taking place in a particular central atom in a molecule, because this will be the toughest part for you, because there are several molecules outside waiting to, you need to propose the theory for them. For that, first you should know what is hybridization, and if you're facing a difficulty, then you should first of all know the number of hybrid orbitals that get generated, and then you must be knowing H first. Now suppose if H is 2, then you fix it off, it is sp. It is sp. If H is 3, please fix it to be sp2. If H is 4, please fix it off it to be sp3. Now what is H? H is nothing but the number of hybrid orbitals generated in a central atom before bonding, in the process of getting readied for bonding. This is what our language, what we are using. So H is nothing but, I would like to underline, number of hybrid orbitals generated. If you know the number of hybrid orbitals generated, then you will know the type of hybridization in the molecule. For example, if it is 2, it is sp. If it is 3, it is sp2. If it is 4, it is sp3. And then continuing it, H is 5, then it is sp3d. And if H is 6, it is sp3d2. And if H is 7, then it is sp3d cube. You must understand. So if anyone is wanting to know the type of hybridization in the central atom, the first and foremost thing is how many hybrid orbitals have been generated. If you can know the number of hybrid orbitals generated, this is for the examination purpose. This is not the way to explain a theory, but I'm just catering to the students who wanted to write their exam. This is, no one will explain like this, number of hybrid orbitals generated, then you can determine hybridization. You must be knowing the molecule, you must be thinking, you should have rational thinking, and then only you can get through, right? But otherwise, no. But let me cater to the examination part, people who are writing the exam. For them, let me tell you that it is, if you wanted to know which type of hybridization is taking place in a molecule or a radical. It can be radicals sometimes. It can be NH4 plus. It can be, it can be anything. It can be SO4 minus 2. It can be SO3 minus 2, whatever. These are radicals, right? Even for them, you should know the number of hybrid orbitals. If H is 2, sp. H is 3, sp2. H is 4, sp3, H is 5, sp3d, 6, sp3d square, 7, sp3d cube. That is how you can basically fix the hybridization in a molecule, you must understand. Now, how the obvious question arises, is there any way out to find out the number of hybrid orbitals? Do you have any formula for that? Yes, I do have a formula for that. Yes?